Good morning, everybody. We're going to spend some time this morning talking about boiler basics. So I'm an energy solutions consultant with our industrial team, and my objective today is to help you guys understand a little bit more about boiler basics and make you guys knowledgeable enough that you become dangerous and ask the right questions to your chief operating engineers, to your boiler maintenance guys, your boiler maintenance suppliers, your boiler chemical suppliers. So this morning we're going to go through a little bit more about our Enbridge programs, which you guys should all be relatively familiar with. Then we'll talk about boiler basics. So we'll go through some energy basics, some steam basics, talk about combustion. We'll also talk about water chemistry. Then we'll take a break, and then we'll shift gears and talk about energy savings opportunities in boilers in our boiler room. Then we'll talk about a limited time campaign that we're offering related to making your boilers more efficient. So let's start off by talking about some of the Enbridge programs. Our DSM program has been in existence for over 20 years. We've been successful by gaining customer trust and implementing great projects by having good expertise, great technical people in our team, and gaining customer trust so we can get those projects through with you guys. We have an auditing process in place which ensures that our calculations and forecasts for energy savings that we provide to you guys are realistic. Our program is shown in a wheel, and we start off by helping you guys with knowledge development, arming you guys with the knowledge with courses like today to help you guys ask the right questions and help make your plants better. We work with you guys on opportunity identification. We help you guys test, energy analysis, engineering analysis. We can help with measurement, choosing the right ways for you guys to meter and implement energy management programs at your facilities. Help turn that information into knowledge so you can go through and execute and develop the business cases to push those projects through. And then when it comes to action and implementation, we also provide financial incentives to help you guys get those projects through. It's shown in a wheel because this isn't a one-time visit or a one-time project. As your processes change, as the economy changes, your energy use changes and your energy needs change, and this is a continuous process, and we're there to partner with you throughout this process. We have helped our customers save over 110 million cubic meters, 20 million kilowatt hours, and just shy of 1 million cubic meters of water in just a 3-year period alone. This helps you guys reduce your CO2 emissions and helps improve your bottom line. One interesting conversation I had with a customer when talking about this improving bottom line, the energy savings is additional just to profit. This is an increase in profit. If you are producing a widget or a part which has a 10% profit margin and we can help you save $50,000 in energy, that's the equivalent of your sales team or your business development team going out and achieving over $500,000 in revenue. So that's another way to spin it for some of the bean counters, that this is straight to the profit side, and there's substantial, if you're working in tight margins, this helps you to become more competitive. Let's talk about a general approach to energy savings. When we talk about how energy comes into the facility, it starts from the meter, whether that's your gas meter or electricity meter. It moves to the energy converter. This could be your boiler system, this could be your your motor, and that's where we're transforming the gas into, let's say, a thermal energy source. We then distribute that thermal energy throughout the facility to some sort of end user. So in this example, it could be a heat exchanger, to whatever the need was that we wanted. So in this scenario, we have hot water. We wanted hot water. At each one of those jumps or handoffs, there can be losses. And the more handoffs we have, the more losses there are going to be. So really, all we wanted was the hot water, and this is the process we had to go through to get the hot water. When we talk about energy savings or an energy saving strategy, we actually should be working backwards. You want to start with the need, whether that's HVAC, boilers, furnace, like process ovens. You need to understand what you're trying to do. If you need to condition a space, you need to understand how much ventilation you need to be doing. If you need hot water, how much hot water you need. And we start saving from the end user. We understand the need, then we start shifting upstream. I've had a customer call me before saying, I want a more efficient boiler. I need a more efficient boiler. Well, he's starting too far up the chain. How do you know you need a more efficient boiler? If all the other downstream processes are more or are wasteful and inefficient, you actually need a bigger boiler. So let's go back to the beginning and understand what you need. Then once we establish what we need, we'll move to the end user and make sure that we do what we need to do in the most efficient way possible. Does that make sense? Once we know what we need to do, we're going to do it as efficiently as possible. And that heat exchanger should be not fouled up, should be clean, should be optimized, sized appropriately. Then we'll take a step and we can move forward towards the distribution system. Are we transferring the energy there in the most energy efficient way or in the most efficient way? If it's steam piping, are our steam pipes insulated? Are we returning condensate? Do we have steam traps that are failing and just letting steam blow through? Then, once we've made sure that we're delivering the energy, then we can start looking at the energy converter. That's where we get into more capital type projects. So you'll also recognize that the dollars associated with energy savings increase as you come closer to the supply side. This energy converter would be then maybe more efficient controls or a more efficient burner, boiler. And then we look at the source of the energy, and that's where you get into things like heat recovery as well. So does the boiler even need to put in as much energy or gas, whatever comes from the meter, because we're doing heat recovery? Does that make sense? So let's go into some boiler basics. I want to start off with energy and a little bit of clarification. This may seem very basic, but I want to make sure we all start from a common page. Energy is defined as the ability to do work. In the boiler room, we typically talk about energy in BTUs or British thermal units. One very confusing part with BTUs is if you put an M in front of it, it means 1,000, and if you put in 2 M's in front of it, it's actually 1 million. So if you hear somebody saying 5 MMBTU, that's 5 million BTUs per hour, which is a little bit different than how we do it in the metric system. A BTU can be defined as the energy required to heat 1 pound of water 1 degree Fahrenheit. So it's actually a very tangible energy unit. Power is the rate at which we transfer energy. How many BTUs we can get through in an hour. And it's defined in BTUs per hour, or if we're on the metric side and talking about electricity, quite commonly kilowatts. The specific energy content, if we want to talk about how much energy is within 1 pound of water or 1 pound of steam, this is sort of talking about enthalpy, and we'll represent that in how many BTUs per pound. So how much heat that water's packing, or how much steam, or how much heat that steam's packing. Does that make sense? So we're going to use these terms as we go through the presentation. Please stop me at any point in time if you guys have any questions. There are a few quick conversions, and we've actually supplied for you guys in your handouts a nice little conversion card to help keep some of these units straight. So if we're talking about boiler horsepower, how much heat's within natural gas, nice little conversion there for temperature and also kilowatts to BTU per hour. Let's jump into steam basics. Now that we've talked about energy, let's go to steam, which is going to get us into our boilers. Water and matter of all forms kind of exists in three distinct states. We have solid, liquid, and gas. Solid being ice, obviously, and gas is the steam that we're talking about. Steam is water vapor that's generated by adding energy into the water, helping it raise its temperature to its boiling point, which we'll talk about more as the sensible heat, and then we actually do the phase change. So we convert those water molecules, we help get them from the liquid state to the gaseous state. We want them in the gaseous state. We want it as steam because steam is an excellent energy transporter. It packs a lot of BTUs per pound, and we can transfer it quite efficiently. So instead of running a hydronic boiler, which some people do, per pound, we can carry 3-4 times as much energy when we're using steam. To put in terms the latent energy versus steam or sensible energy, I have a simple plot here which has temperature on the y-axis, and on the x-axis we have energy. So if we start in the bottom left-hand corner, let's say we had a block of ice. A block of ice could be at -10, -20 degrees C. We start adding energy to that block of ice. The temperature of that block of ice will start to increase until we hit the melting point. This is the sensible heat. It's sensible because we can measure the change in temperature. We can see, as we add energy, an actual temperature rise. This is called sensible heat. Once we hit that melting point, we can keep adding energy and we'll get a two-phase mixture. We'll start to do that phase change. The solid will start to convert into a liquid. We'll keep adding energy, but we won't observe a temperature change. This is called latent heat. It's there, but we can't see it. We can't measure it in terms of what shows up on a thermometer. Does that make sense? If we have that ice and water mixture, we keep adding energy until we have all water. Then when we keep, and this is where we get into the boiler system, if we keep adding energy at the water-only state, again, the water will continue to increase in temperature until we hit the boiling point. So this is all for water at atmospheric pressure. So we'll add energy on our x-axis. We'll see that resultant temperature in the water until we hit the boiling point. As we continue to add more energy, we'll actually convert that water into steam. Again, this will be latent heat. We're not going to see that temperature rise. We'll still sit around that 100 degrees C marker, and we'll have water and steam in a two-phase mixture. We'll have both liquid and gas until we convert all the liquid molecules to gas. On the graph on the side, you can see the relative amount of energy we've added, and that's also proportional to the x-axis. The sensible heat is the small portion. It takes a significant amount of energy to do the actual phase change. And when we use a boiler, that's what we're taking advantage of. The boiler itself is going to do that phase change. We ship the energy via steam to our user, and then we want to extract that phase change back out. So we want to condense and get it back to the water side, or the water phase, and use up all of that energy along that x-axis. If we continue, so now we have steam, all steam, if we continue to add energy, we'll end up with hotter steam or superheated steam, so we'll stay in the gaseous state. So when we make steam, we do two things. We add both sensible heat and latent heat. So if our condensate's coming back at 180 degrees or 190 degrees, first we're going to have to add some sensible heat to the condensate, which is the liquid, to get it to its boiling point, and then we're going to have to add the latent heat to get that phase change. The amount of heat required to get it to or sensible heat is, as we talked about, the amount of energy, that measurable energy that we can see on this thermometer to get it to the boiling point. Then we will move into the latent heat, which, as I said, is the phase change, the energy required to do the phase change. And the latent heat is what the boiler puts into the fluid. We send that fluid to the boiler or to our end user, and we transfer that to our actual load. Returning the maximum amount of condensate is essentially sending as much as possible of the sensible heat back to the boiler. Yes, it's not as important as the latent heat, but we still have put in the energy for that sensible heat that we want to send back. The temperatures at which this all occurs, the boiling point and the melting point, specifically for this course we're focusing in on the boiling point, depends on the pressure at which we're operating. So at 0 PSI gauge, the boiling point for water is 212 degrees F. If we put a lid on this pot of water and turn it into a pressure cooker and let it go to 100 PSI, the boiling point will change all the way to 338 degrees Fahrenheit. So the curve that I showed before with the different states, it still applies, but we shift the temperature. So the actual boiling point is a function of temperature, and that's why when we have different steam requirements or different load requirements, we're going to run different pressures depending on what temperature we're looking for. So you can see the pressure dependency or the temperature dependency is a function of pressure. And so we'll talk a little bit more about 100 PSI steam in this course, and that's just shy of 350 degrees Fahrenheit. The amount of energy in that pound of steam, let's say at 100 PSI G, has two components as we talked about. It has our sensible portion and the latent portion. So you can see in this scenario at 100 PSI G, that's almost 3 times the amount of energy in the latent. We can read these properties from a steam table, and they're represented by HG, HF, and HFG. The H stands for enthalpy, or how much energy per pound we're packing, but instead of just the specific energy content that I spoke about before, H will take into account that pressure as well. So HF is how much energy we have in the liquid. So the saturated liquid relative to 0 degrees C or 32 degrees F, how much energy do we have in the water? HFG is how much energy does it actually take to do the phase change? How many BTUs per pound did we have to put in to get the liquid to go to a gas? And most importantly, when we condense it in our end user, that's how much energy we're going to get back, or we're going to get out of it. HG is the sum of the two. So if you were to throw that pound of steam in the garbage, how much BTUs did you just throw out? You've thrown out both the latent part, which we want, as well as the sensible. So if you have things like failed steam traps and your vent on your condenser or your condensate receiver is just venting steam, you're throwing out both the sensible portion plus the latent portion. We've provided a brief steam table for you guys, and we'll just briefly look at how we use a steam table. And this is important for you guys to know roughly what temperature your steam is at. You can use this to help troubleshoot things in terms of how much air may be in your system and steam quality. So across the top, you'll have PSI gauge. So what pressure steam are we operating at? You'll have it'll say saturated or the saturation temperature. So what is the boiling point at that pressure? Then, as we talked about on the slide before, we'll have HF, HFG, and HG, which is how much heat there is in just the liquid portion, the gaseous portion, and then combined. So if we look at what we talked about before for 100 PSI G, we would go down the first column, find our pressure. So we're looking for 100 PSI G, and now we can determine the properties for steam at that pressure. So the saturation temperature, as we talked about, it's just below 350. It sits at 338 degrees Fahrenheit. To get water from 0 degrees C or 32 degrees F up to the boiling point, we have to put in 309 BTUs per pound just to get it to that boiling point or that saturation temperature. Then, to get that to turn into a gaseous state, we're going to put in 880 BTUs per pound, and conversely, that's how much we're going to get back out when we condense it, if we condense it right back to the saturation temperature. Combined, that's 1,180 BTUs per pound. Does that make sense? Now that we know what steam is, this slide may be a little basic, but I just wanted to briefly introduce the concept of a boiler. A boiler is a closed pressure vessel where we use it to convert potential energy within our fuel, whether that fuel's oil, propane, biomass, biogas, natural gas, into thermal energy. So that's our first kind of handshake handoff. We take the energy in the fuel and we turn it into thermal energy through the combustion process, which we'll talk about next. The thermal energy released from that fuel, we then transfer it into some sort of medium. So in the case of a steam boiler, we transfer that thermal energy into the water. If it's an oil boiler or for a chip fryer, we're transferring that thermal energy into oil. Then, so that's kind of our second handoff. We're going to give that thermal energy from the combustion process to the fluid, and then we're going to send the fluid out to our plant where we actually need that load. Now that we've talked about a boiler, we've talked about steam, we're going to work today with a sample, or this morning with a sample steam plant, and you guys will see this steam plant pop up again. So for our reference today, we're working with a 300 horsepower boiler, which has an input fuel requirement of about 10 MMBTU per hour, and it's on average loaded about 50%. Our plant operates 6,000 hours a year, which gives us an annual fuel usage of 1 million cubic meters per year, or about $280,000 per year based on 28 cents a cubic meter. If this doesn't fit your facility, everything can be scaled relative to this. So if you're a little shy of 1 million cubic meters, the paybacks may be just slightly worse, and if you're over 1 million cubic meters, the paybacks could be on the better side when we start talking about energy conservation opportunities. Let's follow this boiler system around just briefly. So we're going to put natural gas and air in to make our flame, and our flame is going to turn that fuel into the thermal energy we talked about, and the boiler is going to take that thermal energy and put it into our boiler feed water. So we're going to put water into the boiler, take the energy from the fuel, evaporate that water to make steam. Our boiler has a combustion process, and as a result, we have flue gas, which leaves through our stack. We get steam out of our boiler, which we send typically to 2 places: our process, as well as our deaerator. If you don't have a deaerator, you may just have a condensate receiver. You will likely send steam there as well to help ensure that the temperature of your feed water is appropriate. The deaerator is also a pressurized vessel. It'll operate between, let's say, 3 and 10 PSI G. The deaerator has a purpose of stripping oxygen from our boiler feed water. So we've sent processed steam out to the plant. This model plant only gets 50% condensate back. They may have issues of steam traps. They may have live steam processes. They may be injecting steam into a product or onto a surface to extract fibers. So because this is a closed loop system, we have to make up that remainder, and we call that makeup water. This is our softened city water in our boiler room. We typically have a makeup meter on there, and we're taking city water. We either put it through an RO process or soften it. and then put it into our condensate tank or our condensate receiver. Here, we'll ship both of those products into our deaerator, and if you don't have a deaerator, this is basically your output to your boiler. The deaerator does its process of both heating, more sensible heating, to our boiler feed water and the oxygen stripping. Then we will send the boiler feed water to the boiler to be evaporated. Is that straightforward? There's also a process called blowdown, which Mark will speak a little bit more about when it comes to water chemistry. But blowdown is a process we use to control the quality of the water in the boiler, in our boiler system, for obviously maintaining longevity of our boiler system. We also use chemicals. This is a simplified diagram. There's a few things missing, but the gist of it, you can go into any boiler room and kind of find these main components. And these are the components that we need to understand to be dangerous enough to ask the right questions and to start understanding, I would say, what would be the top 4 or 5 energy efficient opportunities you see within boiler systems today. Improvement of boiler efficiency. So we're going to talk about that boiler room, and we're only going to really stay in the boiler room. We're not going to talk too much about downstream processes. This course isn't about steam piping or steam traps. We're focusing more on all those handshakes and handoffs in the boiler room. Improvement in boiler efficiency is achieved by reducing those losses. So with a boiler, we have 3 main losses. Through our combustion process, we have stack losses, which is the biggest loss in your boiler room. We have radiation losses, so the boiler's hot. If you go and get close to it, it feels nice and toasty and nice and warm near the boiler always. This is the smallest of the losses typically. And blowdown losses, when we actually get rid of all the sludge and stuff in our boiler, we tend to send it with heat as well, unfortunately. So we have 3 main losses that we'll talk about today. And we need to understand those losses in order to actually improve the boiler. So we can only make improvements if we're losing energy. If this boiler had no losses, there'd be no energy efficiency opportunities available. So we're going to go through those first 2 losses. We're just going to focus on stack losses and blowdown losses for this workshop. When we understand the losses, then it's quite easy to understand how we're going to achieve savings from reducing those losses. Does that make sense? So that's sort of the logical format moving, or the flow moving forward with the presentation from here is we'll see this slide again and again. We're going to go through stack losses first, then blowdown losses. Then we'll have our break, and then we'll talk about how to save stack losses or reduce stack losses and blowdown losses. So let's start with stack losses. Stack losses are a result of the combustion process. It can be that first handoff where we convert thermal or potential energy in the fuel into thermal. So if we have a poor handoff there, if we have a poor conversion, we're going to have more or less losses, or more losses if it's a poor conversion. We also generate water during the combustion process. The second source of losses or source for stack losses is insufficient heat transfer. So we took the energy in the fuel, turned it into heat, but if we can't get that heat into our transfer medium, the water or the oil, then we're also, that leftover heat that didn't get in there is going to go out through the stack. So if you have a ton of boiler scaling or poor heat transfer surfaces within the boiler, so we're talking about the tubes inside the boiler, then you're not going to extract as much heat as you'd like out of the thermal energy and end up with higher stack losses. Energy that is not transferred into that feed water, the energy that doesn't make it into that handshake before it leaves the boiler, is losses that will leave through the stack. So we want to get as much as of the potential energy in the fuel into the feed water. That's the objective of the boiler. The more efficiently we do that, the more efficient our conversion process is. So perfect combustion, we mix natural gas and air. So similar to your car, we're mixing air and fuel and you have a perfect ratio, stoic. Quite often people say stoic, or you're running lean, you're running rich. So for natural gas, which is mostly methane, we actually put in air, which has oxygen and nitrogen in it. Together, we'll combust these and produce, in a perfect world, we'll produce carbon dioxide, we'll produce water, and the nitrogen just goes for a free ride. So we started with nitrogen at whatever our combustion air process temperature was, and then we send it for a free ride through the boiler, hopefully extract as much heat as we can that we put in through the combustion process, but it just goes along for the ride. It's not part of the chemical reaction, and it doesn't convert. It stays in its gaseous form throughout the combustion process. A rough rule of thumb that you can use by volume is we need 10 parts of air for every 1 part of natural gas fuel. So that's sort of 9.5 is our 9.52 to be exact, with pure methane is what we would call stoic for combustion. If you have less, we're going to be running, you would have incomplete combustion, and if you have more, you would have excess air. When we burn 1 cubic foot of natural gas, the potential energy that we have in there that we're trying to extract out, just for reference purposes, and I do believe it's on your card as well, is 1,012 BTUs per pound, or sorry, per cubic foot of natural gas. I want to talk about that mixture and that balance with this plot. If we had flue gas losses, or how much energy we send up the stack on the y-axis, as a function of how well or how much air we're mixing with the fuel, this plot will show us a little bit of that relationship. So if we say at stoic, our perfect mixture, that 9.52 parts of air per part of fuel, we have basically minimal or no losses, and that's our maximum efficiency. If we have less air, with natural gas, we end up with incomplete combustion. We start producing carbon monoxide, and we also start exponentially increasing our flue gas losses. I would say this is somewhat analogous to running rich in your car. We have more fuel than we do for parts of air, and as a result, we have incomplete combustion. And this is also a safety issue when it comes to boilers and natural gas combustion. If we start from stoic and work the other direction, we call this excess air, or high O2, high oxygen levels. As we move away from that perfect mixture, that 9.52, and start adding more parts of air, we get complete combustion, which is what we want. But if you send too much air through, you actually end up with exponentially increasing flue gas loss or stack losses. So we send extra air through the combustion process, which takes heat to heat up. We got to heat up that air. It goes for a free ride because we have 7.52 parts of nitrogen in there. That's just going to go out through the stack. So there's a fine balance, and ideally, we want to operate just on the right-hand side of that stoic point. You definitely don't want to be on the left-hand side. We always, with natural gas, err on the side of excess air, and some companies have a policy of how much minimum excess air or oxygen that you need to have. But ideally, you want to be on the right-hand side, but as close to stoic as your burner, this is boiler and burner and process dependent, will allow you. So when these guys are tuning your boiler, they're trying to shoot for this, keeping in mind the safety side. So we're going to err on the safe side, so we're going to push a little bit of extra air through. The safer we are in terms of, or the more extra air we throw through, the more losses we have. So it is a fine balance. That relationship, that exponential relationship on the right-hand side with combustion excess air and combustion temperature and the losses is shown on the combustion efficiency chart that we gave you guys. This chart is the relationship between that excess air and the losses. So we can, on the left-hand side, going down the page, we have how much excess air or O2 we have. And across the top, across your columns, we have really what we would call a delta T, which is the flue gas temperature minus the combustion air temperature. So wherever we're pulling that air from, if it's already at 150 degrees, or if it's at 60 degrees Fahrenheit, you would take your stack temperature and minus your combustion air temperature. What this chart shows you is that if we look at excess air, this is what we talked about. As we proceed further down, more excess air or higher oxygen, we get decreasing efficiency. So if we look at 400 degrees, at 3% O2, we have 81% combustion efficiency, so 19% losses going through the stack. If we put 4% more oxygen, or almost more than, or 3 times as much excess air, we go down to 79% efficiency. So that goes with the curve we showed you, and this is just sort of the tabulated version of that curve, which we can use to evaluate the efficiency of our boilers. Similarly, across the top, we have increasing flue gas temperature. And you can see if you go from 300 to 400, you also have decreasing efficiency, which makes sense. The hotter our flue gases are, the less energy we transferred into our medium, and thus the less efficient we are. Does that make sense? So if we use that chart and we had a boiler that had excess 2 of 8%, flue gas temperature of 460 degrees Fahrenheit, and combustion air temperature of 80 degrees Fahrenheit, this is just a snapshot from your chart. You can go and find those 2 points. So we would calculate first our delta T, and then we can go through and find 380 degrees and that 8% to see that we're operating at 78.9% efficiency. That means of the 100 units of fuel or potential energy in that fuel, we've successfully extracted 78.9 of them into the boiler. The other 21.1 are going up the stack. So how does this relate to you guys? Well, I'm assuming either annually or semi-annually, you have your boiler maintenance supplier do a combustion strip for you. So let's take a quick minute to look at that combustion strip, because everything we've just talked about in that table, this is how we get that information. We can take that strip that we get from them, and instead of just filing it until next year, I can show you guys the information we want to look at on the strip that can help you ask the right questions. So the strip comes out of a flue gas analyzer, which will tell us a few things. It'll have our flue gas temperature. If the supplier has input your combustion air temperature, it'll actually spit out the delta T here at the bottom. Otherwise, you can assume it's 80, 90 degrees. If your boiler room's on the warmer side, maybe it's close to 100, but 70, 80 degrees is a fair average annual combustion air temperature. So it's going to measure the temperature in the stack. It's also going to do a chemical analysis of how much oxygen's in there. So now we know where we are on that chart. We have our flue gas temperature, and this guy's running 10% oxygen. So now we know how much excess air, which is also shown here. So they have 80% excess air. So we're operating quite a ways up on that curve that we talked about. It'll also tell us carbon monoxide. So if we're on the other side of the curve, if we're not supplying enough air, or if our burner has poor mixing capability and we need to supply a lot of extra air, this will tell us how much incombustibles we have here and here by how much carbon monoxide we're producing through the combustion process. In the end, it will do that lookup on the table for you, so you don't even have to go through and do that, and spit out a combustion efficiency. So you know where you are on that table. So this person is extracting 76.5 of the 100 units that we put in fuel into their boiler. So there's some room for improvement because we're sending 80% excess air. Typically, you guys are having maintenance suppliers come in and do this for you. We can also support if you don't know where you are and need to understand where you are for moving forward in terms of energy efficiency improvements. This is where a Flue Gas Analyzer, which we have, we can come in and look at your boiler and produce that strip for you. So we can go in, work with you. You need about a 1/4 inch hole in your stack, and we slide the Flue Gas Analyzer in, and we move through, ideally we move through the firing range, so sort of the gas pedal of the boiler, and take the efficiency readings. Is that clear? Some typical readings, just to give you guys a rough idea of where you should end up and things to look for on the strip. This is by no means a rule of thumb. This is rough numbers to help you guys ask some questions if you see something. Your flue gas temperature, and the reason we gave you that steam table, should be roughly 100 to 125 degrees above the saturation temperature of steam. So if we say 100 PSI Gauge steam is roughly 350, we should see a boiler, if you don't have an economizer, we should see flue gas temperatures in the 450 degree range, which for heat exchanger people, it's basically a 100 degree approach roughly when they design a boiler. If there is a feed water economizer that's functional, you should be much closer to the temperature of your saturation. So roughly 100 degrees below where you would expect to be. On average, a feed water economizer will pull out 180 to 120 degrees F from your flue gas temperature. When it comes to oxygen, we'd like to see this in the 4 to 6% range, especially towards high fire. Depending on the burner design and the mixing capability, this may need to be higher. And we would expect that at lower firing rates, so when the boiler's closer to idling, that this will be higher. It's not uncommon to see 7, 8% at low fire, but we want to target that 4 to 6% range when we're kind of sitting around that 80%, 50 to 80% cruising point where you're operating. That 4 to 6% means we're kind of slightly to the right of stoich. So we're in a safe region, and the tuning guys aren't going to go much lower than 4 or 3% because they don't want you to drift into an unsafe region. If you happen to see carbon monoxide ppm levels on your combustion strip, this can be a safety concern. I would say I would ask more questions to both the tuner, and if you have a chief operating engineer, I'd be asking questions if we're over that 200 ppm. Ideally, you saw in that combustion strip, when we have lots of excess air, we should have complete combustion, and we should have very little carbon monoxide ppms generated. So 100, 150, but if in that range, I would be asking questions. And like I said, this is by no means a rule of thumb. This is, if you guys get these strips, you don't have to just follow them. You can use this slide. This presentation will be available online, or you can ask your ESC for it. This whole workshop will actually be available online, and you can rewatch me talking about this slide if you want. And you can use that to read the combustion strip and ask the right questions. Now that we've talked about stack losses, I want to move into blowdown losses. So for blowdown losses, I'll invite our commercial ESC, Mark Kamasuli, up to talk about it. Mark is a water treatment specialist, so we'll let him speak to blowdown losses.
All right. Morning, everybody. So As far as blowdown losses go, I'm going to give you a bit of an overview of the chemistry behind what's going on in a boiler as well, because these things all tie into efficiency and the way that your boiler is going to operate. I think later on you're talking about blowdown, heat recovery, and whatnot, so we're not going to touch on that right now. So we're back to this slide here, and what I wanted to show you in this particular slide is, we talked about the enthalpy and the energy that's going around in this cycle, but behind that there's also the chemistry. So when you're bringing fresh makeup water into the system, into your condensate tank or your feed water tank or to your deaerator, wherever it's being injected, you're not just bringing in water. That would be nice, but generally speaking, your water is coming out of the municipal water system, and that water came from somewhere. In Toronto, it's coming from, or in the general GTA, it's coming from Lake Ontario. The water here is pretty good. It's pretty pure water. It's not too hard, but it's got minerals in it. It's got calcium and magnesium and carbonates and bicarbonates and chlorides and all sorts of other smaller constituents that are in the lake. Of course, it's purified by the water treatment plant for drinking purposes, but that stuff is still in there. If you're in an area where the water is coming out of the ground, then you're getting all the minerals that are in the groundwater. So, if you're up on the Bruce Peninsula or somewhere up there, it would be, I know nobody in here is, but you would be dealing with all sorts of hardness minerals. So we got to worry about what's going on in there, because that stuff has a significant impact on what's going on in the boiler system. That, of course, comes into your condensate tank, through your deaerator, ultimately into your boiler. Now, a boiler functionally is a big distillation process. So when you produce steam by adding that heat and going through your sensient heat and up through your latent heat and producing steam that leaves the boiler, all that mineral that was in there and that was all in that fresh water stays in the boiler. It doesn't evaporate. Calcium and magnesium aren't volatile. They want to stay in that water that's in the boiler. So the only thing that leaves the boiler is steam, H2O, and some gases. So if there's any dissolved gases in the water that came in, like oxygen, carbon dioxide, and whatnot, that'll leave with the boiler steam as well, which will then go out through the network. You're going to use it to heat processes and whatnot. You're going to capture some of the condensate that forms, and maybe some of it is live steam. In this case, we've got 50% condensate return. So 50% of the steam that leaves this boiler is gone. Well, you've left all the minerals from that 50% in the boiler. And now you've got to make up that water, right? There's level controls in here that are keeping the water level in the system steady. So you're adding, so for every gallon of water that you sent out here, you get a half a gallon back, which means you need to add a half a gallon here, which means you're adding all the minerals that were in there. And what that does is it has a concentrating effect in the boiler. And the way I kind of look at it, and a good sort of comparison, is if I had a coffee cup and I left it on my desk at work and I went on vacation for a couple of weeks and I come back and it's all evaporated, I've got this coffee crud at the bottom of my cup. Now, if I'm kind of a disgusting person and I decide I'm not going to wash that cup, and I go back into the cafeteria and I fill it up with coffee, what do I have now? I've got double concentration, rather gross coffee. And let's say I get sick. I leave that cup, I haven't drank it yet, I get sick, probably because I took the first sip of that coffee. I go away for a couple of weeks, I come back, I do the same thing, fill it up again. I now have triple concentration coffee. Well, that's functionally what's happening in your boiler. So all those minerals that are coming into the system, concentrated up every time that volume of the boiler is replaced. So this is essentially what's going on here is when water's boiled, steam is generated, all the solids stay behind. We have to, at some point, drain water out of the boiler, and that's what blowdown is all about. The solubility of those minerals in that water has a limit, right? You can only dissolve sugar in your coffee for so long. I like the coffee analogy this time of morning. So you can only dissolve sugar in coffee so long. You're going to hit the saturation point. You're going to keep adding sugar. It's going to sink to the bottom. Same thing happens in a boiler. Those minerals will concentrate up to a point. They can't concentrate it anymore. And so we have to control that. And so we have In most modern boilers now, it's an automated process, right? You've got a probe in your boiler that's detecting the mineral concentration and draining just the right amount of water out of the boiler to control that. There are two types of boiler, bottom blowdown and surface blowdown. I'd say that's changing. It depends on the type of boiler that you have. In the old sort of fire tube boiler, those made perfect sense. I mean, you had bottom blowdown because some of the solids fall to the bottom. Maybe every day a guy would just come down and open a valve to drain that stuff out. Surface blowdown tends to be the one where we're controlling the dissolved solids concentration in the boiler. It's a continuous process. I've certainly seen places where they have a valve and the guy just adjusts the valve and tests the water once in a while, adjusts the valve. Much better to have an automated technology. It's not expensive. I'd say most decent boilers these days actually come with it. But if you don't have it, you should look into it. Now, from an energy perspective, when it comes to blowdown, there's detriments on both sides of the spectrum. So if you don't have enough blowdown, you're going to have a couple things happen. You're going to have those solids that can't stay dissolved in the water anymore sitting in the boiler, and they're going to stick to the tubes and they're going to create an insulating layer. So now when you try to heat that water with your combustion process, it's not only dealing with, you know, maybe a fraction of an inch of the metal pipe that is the tube in the boiler, but it's also dealing with this insulating layer around it. So now it's putting more energy into the pipe in order to try to turn that water into steam, which means your flue gas temperatures are going to go up. You're going to losing all sorts of energy from that. So there's actually a connection there between blowdown losses and flue gas losses. On the other hand, you could just drain lots of water out. Let's not worry about that anymore. Let's just open a valve and we'll use lots of water. We'll make sure we're not going to get any solids depositing in the boiler. Well, now you've got excessive blowdown. All that water that you're putting down the drain is hot, right? If you're in a 100 PSI boiler, it's 338 degrees Fahrenheit. You send that down the drain, you're sending water, you're sending chemicals, because you've added chemicals to the boiler, which we'll talk about briefly in a bit, and you're dealing with the energy that you put into that water. So excessive blowdown is a significant loss of energy as well. The range, the percentage of blowdown varies dependent on a number of factors, predominantly the water quality that you're bringing into the system. Like I said, you've got a lot more minerals in groundwater, which means you can concentrate that boiler up less times than you could if you had nice pure water coming into the system. So in Southern Ontario, I'd say typically, you know, GTA, we're probably concentrating that water about 10 times before we have to drain some out of the boiler. I know if you were up in Guelph, it's probably no more than 4 times. So you're putting a lot more water down the drain and chemicals and fuel associated with blowdown. The other thing, it varies based on, because we're saying here, typical range is 3 to 6% of feed water. Well, feed water is a combination of your returning condensate and your fresh water. So if you're bringing lots of condensate back, condensate is H2O, right? It's nice pure water, it doesn't have the minerals in it. So the more condensate you bring back, the less blowdown you're going to have to do. Boiler is a really aggressive environment. High temperatures, you've got water and metal in contact with each other, predominantly steel. There's a tendency, you know, even in your backyard, you got a steel chair and you got water and oxygen in the environment, you're going to have rust, right? Well, in a boiler, it happens much more aggressively. And we call this oxygen pitting. So what happens is, you know, the start of that reaction where a little bit of oxygen made contact with the metal and there was some moisture there, you got a corrosion reaction, and I'm not going to get too much into the chemistry of it, but it happens in a very localized way in a boiler, and it will drill its way through those tubes pretty quickly if you've got a lot of oxygen in your system. So this can cause boiler failures. Mineral deposits and scale on boiler tubes, well, that can certainly cause a failure, but it's also you're dealing with the efficiency and that insulating layer I was talking about. So we have 2 major concerns certainly with regard to mineral deposits. And then of course, if the boiler fails, you've got downtime, you've got all the costs associated with running your operation. So this is something we definitely want to avoid. carryover of boiler water into the system. So if we allow that concentration in the boiler to continue to rise and rise and rise, and we don't do the blowdown soon enough, not only are we going to have minerals coming out of solution and sticking to tubes, but we start to get foaming in the boiler, and we get water actually leaving the boiler. So no longer are we just sending gaseous water as in the form of steam. We're now sending boiler water out with it. And there's a whole bunch of negatives that come along with that. One is you've got droplets of water moving at very high rates, because steam moves fast through a pipe. We've now got water going through that pipe with it. And if there's a bend in that pipe somewhere at an elbow, that water hits that elbow at a really high rate and actually has an abrasive effect and can eat through your elbow. It can cause all sorts of problem with steam control, pressure control equipment, and whatnot. The other thing is, from an efficiency standpoint, if you've got water droplets in your steam, I mean, the reason we are using steam is to carry large amounts of energy through a small pipe and use it as effectively as possible in a process, right? We're looking for that latent heat of vaporization. That's the energy we're looking for. If you got water in there, the latent heat in the steam is now trying to evaporate the water and turn it into steam. And so there's this battle going back and forth. So you actually have to send more steam out into your plant in order to do the same amount of work. And it's a waste. So we want to avoid doing that as well. There's a graphic of really bad oxygen pitting, and it doesn't take long. It really doesn't, especially in our modern boilers. We've gone from the old beast fire tube that you could kind of beat up and not have too many negative implications from, to these more modern, efficient, low water content boilers. Much thinner tubes in order to be more efficient, but that also means it takes a lot less to cause problems. And then this is just a graphic of the inside where you've got mineral scale. So you've got, the water level in here is probably up in here typically, and you've got all this mineral scale. And now we're not even seeing down into the tubes where the fire is. So this is going to be even worse. Like, this is just the steam drum up top. But you can see all this minerals sticking to the tubes. This is predominantly going to be calcium and magnesium, which are, calcium and magnesium and iron are your minerals that make up hardness. We soften water going into boilers at the very least. I think you mentioned before you may do reverse osmosis or other types of pre-treatment to take out those minerals. Those minerals are a little bit unusual in the sense that they become less soluble as water gets hot, as the temperature goes up. So you can dissolve more sugar into a cup of coffee the hotter it gets. It works the other way around for calcium and magnesium. They get less soluble as the water temperature increases. So what that means is the hottest spot in that boiler where that flame is hitting that tube is where that magnesium and calcium want to stick. So we got to make sure that stuff isn't in there in the first place, which is what we do when we have water softening systems. Before I get into this for too much, the other thing we do as far as prevention of these sludge deposits. So again, we've got control of the dissolved solids concentration through blowdown, and we've got pre-treatment of the water to take out all these minerals. We also tend to add polymers to bind up those materials so that if something happens, if there's a little bit in there, we have control of that and we're not going to cause ourselves any problems. So it's sort of a secondary backup plan, if you like. This is kind of what you're going to see from your water treatment supplier, is some version of this kind of report. I'd say they're all fairly similar. There are some sort of less common technologies in use, but for the most part, I'd say 95% of the water treatment companies are using similar types of technologies, similar types of chemicals. The blends may be a little bit different, but ultimately they're going to report it in a similar way. And I think when people are faced with this table, if they don't really understand what they're looking for, it's easy to kind of gloss over it and not really focus in on the important stuff. So I just kind of want to go through the report briefly and say, here are the things you're looking for. Here are the key elements. First thing up there is hardness. So again, your calcium and magnesium, and technically your iron, although that doesn't play a big role. So your water treatment company, and hopefully the person taking care of your boilers as well, is going to be regularly testing the hardness level coming out of the water softener. And then the hardness level within various points throughout the system, in your boilers, your feed water tank, or your deaerator, if you've got separate condensate tanks. Certainly if you're dealing with a system that's got heat exchangers that are heating water for a process or domestic hot water or something like that, you want to be testing the hardness levels in your condensate as well, because if a heat exchanger has a pinhole in it, now you've got potentially unsoftened water coming back to the boiler system through the condensate. Now that'll of course show up back here again, because if you remember that whole loop, your condensate comes back to your boiler again. There's also going to be some limits shown along the bottom as far as what we're targeting. Now typically you're looking for a 0 here, but the chemical tests that you're doing, or that your operator is doing, or your water treatment company is doing, have some error to them, so there's usually a bit of a range. And again, you've got polymers in there. Your polymers are protecting you as well. So you get a little bit of iron in the system, you might get a 2 or a 4. It's probably not a big deal. So I'd say this is sort of a typical range. Talking about oxygen pitting, sodium sulfite is added. And you may recognize sulfite from red wine. Often red wine in the bottle, it says may contain sulfites, or contains sulfites. It's actually doing the same thing. It's an oxygen scavenger. Restaurants spray it on salad bars to keep the lettuce from browning. It's an edible product. And it's added to steam boilers to take out the oxygen, right? If you're worried about corrosion and you've got water and metal and oxygen together, if you take out one of those, you're going to eliminate your problem with corrosion. So we take out the oxygen. Trevor mentioned we often will steam heat the feed water tank or even have a deaerator. That is a mechanical process designed to take oxygen out of the system to prevent corrosion. We would still want to add a preventative amount of sulfite as a scavenger, but ultimately your objective is get rid of the corrosion problem. And again, you're going to see limits on here. I'd say these are sort of fairly typical limits, 50 to 100 parts per million of sulfite in your boiler system. pH. Carbon steel likes a pH in the range of probably 8 to 12. Water coming out of the ground is probably in this area just below or around 7. I think it's just below 7 typically. There are minerals in the water that when concentrated, which we're doing in the boiler, raise the pH. And you can actually do this, like if you put a pot of water on your stove at home and let it boil until it's 30% of the volume, the pH will go up to 12 because of the minerals that are in that water. So we typically watch for the pH in the boiler, but this is actually a naturally occurring process. When we concentrate the boiler water, the pH rises. And that's a typical range that you want to see in a boiler. That's an ideal range for carbon steel, which is what most of the boilers are made out of. Conductivity is just our way of measuring those dissolved solids concentration. So we're concentrating up that water in the boiler. The best way to know what the dissolved solids concentration is to take a sample of water, evaporate off all of the water, and weigh before and after, and then you've got a comparison of your dissolved solids concentration. Obviously, that's not the most practical thing in the world. So we use conductivity, which is just that water's ability to transfer electrons as a measure of dissolved solids concentration. So 3,000 to 4,000, again, there's a lot of variables that go into this. These are typical numbers. Your water treatment supplier is going to be the one that sets these things and knows the finer details behind what's going on there. But you want to make sure that the number you're seeing on your report is in the range of the limits that have been determined. And if you've got that automatic blowdown control from your boiler, it's keeping it in that range. Alkalinities are usually going to be on there as well. Those are the minerals I'm talking about that bring the pH up. So they're a naturally occurring thing. We're not adding anything there, but those will usually show up on there. A pretty wide range, 150 to 700 is kind of a typical range. So we're not too worried about that. I think in most cases it's going to stay within range. And if it falls outside of the range, you're probably going to have a chat with whoever's doing your water treatment, see if something can be done to improve on that. Now, I did say we weren't going to get too much, or you said we weren't going to get too much into what's going on outside of the boiler room, but one thing to be aware of is I mentioned that when you produce steam from the boiler, any gases in that water also leave. Well, there is a reaction that happens inside of the boiler that produces carbon dioxide. Carbon dioxide travels with the steam. When the steam recondenses, when it gives off its latent heat into a process and turns back into water as condensate, the carbon dioxide dissolves into that condensate. And what it does is it produces carbonic acid. So water treatment companies will typically add something called an amine, or some people say an amine, to neutralize that acid in the condensate network. If you didn't do that, you're going to have pHs probably in the 3 to 4 pH range, and you've got carbon steel pipes all over the place. So if you do that, you're going to corrode your carbon steel pipes, and you're going to have a short life, and you're going to be replacing pipes all the time. So by adding this amine, they will neutralize that condensate pH, and actually I've got this circled as the iron, but that's not even on here, but the condensate pH will typically be on there. And you want to see it in that same range, sort of 8 to 12. It'll typically be around 8, I would say, in your condensate network. This iron number is just an indicator of if corrosion is happening, right? If you've got corrosion, then you've got iron coming back in your condensate, and you know that you've got an issue. If there's anybody here in the dairy industry, it's not amines. You actually can't add amines in a dairy, but they will use ammonia as an alternative to that. So functionally does the same thing. There are also other options, but we're trying to do a sort of a quick overview here. I'm doing my best. Other things you're going to see on your water treatment report, makeup water meter readings, right? You know how much water is being added to the system. That is what's actually being used to control the amount of chemical that's being added. There's usually a water meter tied to a control panel, tied to a chemical pump that's keeping all of that stuff connected, right? So you add a gallon of water, you need to add a certain amount of chemicals. You're also hopefully going to see historical water meter readings, maybe even a graph, depends on the report, which is a great indicator of, could be an indicator of lots of things. Maybe you've got a problem. Maybe there's condensate being lost because a GFI on the condensate receiver tripped or something like that, and now it's going to drain. I mean, I've seen all sorts of different versions of that. But if suddenly your water usage peaks, you know there's something going on there, and you can start investigating. Maybe it's process. Maybe you can say, oh yeah, we produced twice as many widgets last month. That makes perfect sense. Okay, so you're seeing the results of that in your water meter readings. Natural gas meter readings. Again, we're here to talk about efficiency. There should be as much data on this report as you can gather, right? And in an ideal world, every steam boiler has a gas meter on it, but we don't live in an ideal world. Very often they don't. You've got a gas meter for the gas coming into the plant, and that's it. The boiler's probably a pretty large percentage of your gas consumption, if not all of your gas consumption. So you should be able to draw a correlation between the gas being used and the makeup water. Feed water temperatures. There's a few sort of variables that go along with this, but the key one from a water treatment perspective is that oxygen content. We want to keep that feed water temperature up so there's no oxygen in the boiler. It also has effects on the combustion efficiency. It has effects on thermal shock. If you send cold water into a hot, steamy boiler, you could cause some damage. And you're going to see chemical inventory, rates of chemical consumption, that sort of stuff. So I think that's it for me. That's a pretty crazy crash course in water chemistry for 10 minutes or 15 minutes or whatever that is. But any questions at the top of your head while I'm up here? I'll be here all morning. So, all right.
Thank you, Mark.
Thanks, Trevor.
So before we jump into energy savings opportunities in boilers, we'll take about a 10-minute break right now. So if you want to hunt Mark down for some questions, or myself, we are here all morning. But grab some coffee, snacks, and we'll sit back down in about 10 minutes to change gears into how we can, now that we understand where the losses come from, let's go on a bit of a hunt to see how we can actually reduce those losses and improve our boiler efficiency.